Hello and welcome to Math with Mrs. Becker. Today in College Trig, we are going to go through the worksheet that was assigned yesterday where we are practicing how to prove trig identities. I will go ahead and just go through each question so that way you can kind of check and make sure that you are understanding. Remember the front side, it was kind of the basics, so hopefully that's where you started when you were working on these problems on your own. It's just kind of getting used to the process. Just some little tips. What you want to do is try to get the left side to match the right side, okay? So you will never change the right side. You will change and manipulate and maneuver that left side until it matches the right side. And the way that you do that, and this is just from our notes from yesterday, you will use these fundamental trig identities. Now the top, hopefully you're getting comfortable with. Those are our reciprocal identities, remembering that the sine and the cosecant are reciprocals. So you could replace the sine of theta with 1 over the cosecant. You could take the cosecant and replace it with 1 over the sine. Same thing with cosine and secant and tangent and cotangent. Okay, the quotient identities. In order to get the tangent, you could do the sine of theta over the cosine of theta. Now remember, the cotangent is the reciprocal of the tangent, so it would just be flipped around. So the cosine of theta over the sine of theta. Then the other identities that we looked at were called Pythagorean identities. Now notice you do have exponents of 2. When you have sine squared of theta, what it actually means is you had sine of theta squared. So sine of theta times sine of theta. Now remember, you can rearrange these. So if I wanted tangent squared of theta by itself, I could minus that 1 over. So I would be able to replace a tangent squared of theta with a secant squared of theta minus 1, okay? Let's go ahead and just work on the front side. One of the things that always helped me as I was starting to learn how to do these trig proofs is I think it's easier if you can turn everything into sines and cosines. Typically, that's where I start. And after class today, I would say that was the most common question. Most people said, once I get started, I'm okay, but I don't know where to start. So my best piece of advice is start off by trying to figure out how you can turn all of the trig functions into sines and cosines. So let's look at number 1. I have a cosine of x. Okay, so I'm going to leave that. Secant of x. Secant is the reciprocal of the cosine. So what I can do is I can write it as 1 over the cosine of x. Now when I look at this, this is a product. I have a cosine on the top and I have a cosine on the bottom. They will cross cancel, leaving me a 1. 1 equals 1, so you're done. You just proved that the cosine of x times the secant of x is actually 1. Okay, here's another one. Sine of x divided by the cosecant of x, they want you to prove that that's actually sine squared of x, meaning sine of x times sine of x. You would have 2 of them. Again, when I take this side, I want it to be all sines and cosines. So I'm keeping the top sine of x. The cosecant of x, that's the reciprocal of the sine. So I can write it as 1 over the sine of x. Now here, notice what we're doing is we're dividing a fraction. Remember, you can't divide a fraction. So what I do is I keep the numerator the same, the sine of x, change divide to multiply. Now you need to do the reciprocal of the bottom. If I take 1 over the sine of x and I flip it, I would end up with the sine of x. The sine of x times the sine of x is sine squared of x. That's what they wanted us to prove. We're done. Okay, next one. Now here again, I see that I have cotangent of x over tangent of x. They want me to have tangent squared of x. So this time when I look at what my final answer, what they're looking for, they want it to be a tangent. Well, I know that this is a tangent. I need 2 of them. Cotangent is the reciprocal of a tangent. So I can say 1 over the tangent of x divided by the tangent of x. So all I did was change cotangent of x into 1 over a tangent. Again, we are dividing fractions. You can't divide a fraction. So you keep the top the same. It's 1 over the tangent of x. I change divide to multiply. I need to do the reciprocal of the bottom. Right now, the bottom, the denominator was not a fraction, so it's the same thing as saying I had tangent of x over 1. If I flip that, I would have 1 over the tangent of x. Now, when you multiply fractions, remember it's top times top, bottom times bottom. 1 times 1 is 1. Tangent times tangent would be tangent squared of x. That's what we were trying to match. We got it. Okay. Next one. I see that what I'm looking for is my final answer to have sine and cosine. Cosecant and secant, neither of them have sine or cosine right now. So I'm going to go ahead and rewrite them in the form that does have the sine and cosine. Cosecant is the reciprocal of the sine. Secant is the reciprocal of the cosine. Now, when you multiply fractions, top times top, 1 times 1 is 1, bottom times bottom, sine of x times the cosine of x is sine of x, cosine of x on the bottom. That matches. You're good to go. Okay, next one. We have cotangent of x over secant of x. I want to prove that this is the exact same thing as if I had a cosine over a tangent. So the first thing I'm going to do is take this side, write it as sines and cosines, and see what happens. Cotangent is the cosine of x over the sine of x. The secant is 1 over the cosine of x. So if I go ahead and look at this, you cannot divide fractions. I keep the top the same, cosine of x over the sine of x. I change divide to multiply. I would flip this upside down and it would become a cosine of x. As a fraction, that would be the cosine of x over 1. Well, check this out. Cosine of x times the sine of x, that's a cotangent of x. Times, this is a cosine of x. Well, I don't have it matched yet. I need a tangent. Cotangent is the reciprocal of the tangent. So 1 over tangent times the cosine of x. Now I can go top times top, bottom times bottom, and I end up with the cosine of x over the tangent of x. Now at this point, I think it's important for you to realize that there are a lot of different ways that you could do each of these problems, as long as you are using these fundamental trig identities and you continue to work on one side until you get it to match the other side. There are numerous ways that you could approach this problem. And the reason why I thought that after this one is because I know in class today I did this a whole different way. But I used the identities and I kept working until I got cosine of x over tangent x. So let's say you did quite a few of these problems, and as we're going through this, you ended up proving it, but maybe you did it differently than I did. It does not mean that you did it wrong. Okay, I'm just showing you one method of how this works. Okay, let's keep on going. I want to prove that the secant of x over the cosecant of x is really the sine over the cosine. The secant is 1 over the cosine. The cosecant is 1 over the sine. You can't divide fractions, so I keep the numerator the same, change divide to multiply, flip the second one upside down, which brings the sine of x on the top. Top times top, bottom times bottom, I have the sine of x over the cosine of x. That's what I wanted to match, so we're done. Okay, next one. I want to prove that the tangent of theta times the cosine of theta is equivalent or equal to the sine of theta. Tangent is sine of theta over cosine of theta. Cosine of theta, I'm going to keep it. The reason why is because when I look, I see that I could cross cancel the cosine because I have one on top and one on bottom. That leaves me with the sine of theta on the top. The sine of theta is what we wanted to prove. Sine of theta equals sine of theta, so you're good to go. So the only thing I had to do on number 7 was know that the tangent could be rewritten as sine over cosine. Okay, next one. 1 over the tangent. Well, 1 over the tangent is the same as the cotangent. The cotangent is the same as the cosine over the sine. So there are times where you have to go ahead and change things twice. I had to know that 1 over the tangent of theta meant do the reciprocal of tangent, which is cosine, Then from there, I could turn it into sines and cosines by knowing that the tangent of theta is the same as the cosine of theta over the sine, times I'm multiplying it by the cosine of theta over the sine of theta. Now when you multiply fractions, top times top, bottom times bottom, cosine times cosine is cosine squared of theta, bottom. Sine times sine is sine squared of theta. That matches, and you're done. But again, in order to do this one, you had to be comfortable changing 1 over tangent into a cotangent, and then cotangent into cosine over sine. Next one, secant. The secant is the same as 1 over the cosine of x, because that's the reciprocal. The cosecant is 1 over the sine of x. You cannot divide fractions, so I keep the top the same. Change divide to multiply. Flip the denominator around, so now I have sine of x over 1. Top times top, bottom times bottom, leaves me with the sine of x over the cosine of x. Now they don't match right now. This is the tangent of x. But if you look back at our rules, the tangent of x, or tangent of theta, is the same thing as sine over cosine. So if this is the sine of x over the cosine of x, that is the exact same thing as the tangent of x. Next one, I want to prove that the tangent of theta times the cosine over the sine is really equal to 1. Tangent is the sine over the cosine. I'm multiplying that by the cosine over the sine. When you are multiplying fractions, that's when you are allowed to cross cancel. I have a sine of theta on the top, and I have a sine of theta on the bottom. They would cross cancel. Cosine of theta on the bottom, cosine of theta on the top. They would cross cancel. When everything cross cancels, what you have left is a 1. 1 equals 1, and you're done. 2 more, and this again is the basic side. This is the difficulty that you will see when you get to the test, when we take the mid-chapter test. Okay, so if you are feeling comfortable on this side, feel pretty darn good. When we flip this worksheet over, those were the challenge questions. Those are the questions that are getting us ready to factor trig functions and getting us ready to solve equations. So yes, they're definitely going to help us as we move forward. But if you're thinking about the test that's coming up, if you understand this side, feel pretty darn good. Okay, 2 more, and then we'll flip it over and go to the challenge. The cotangent is the cosine over the sine. The secant is 1 over the cosine. Again, I'm multiplying fractions so I can cross cancel. Cosine on top, cosine on bottom. That leaves me with 1 over the sine of x. 1 over the sine of x, this means take the reciprocal of the sine. Well, the reciprocal of the sine is the cosecant of x, and you're done. Last one like this. Okay, when I go ahead and look at this problem, I went ahead and right away changed the cotangent, because remember I said I think it's a lot easier, at least for me, to look at everything as sines and cosines. On the top, I left sine squared of x. Cotangent is cosine of x times the sine of x. Now that is actually going to help me, because if I look at this, I have a sine, actually I have 2 sines. I have sine squared of x on the top, 1 sine of x on the bottom. So I can cancel 1 on the bottom with 1 on the top. That leaves my numerator at the sine of x, cosine of x. The bottom is cosine of x. I have a cosine on the top, I have a cosine on the bottom. I can cancel those out. I have cosine of x, and I'm done. So again, these 12 questions, really, it's just kind of to gauge how you are doing, just starting. How do you prove trig identities? If you understood these 12 questions, give yourself a pat on the back. You're doing awesome. Okay, now the back side, these are a little bit more challenging. They're getting you prepared for what is coming up. It's the same thing. It's just that it's going to be quite a few more steps. You want to keep the right side the same. Change the left side. Okay, and I'm going to go ahead and write on paper so I can write a little bit bigger so it's easy to read. I do feel that it's easiest to turn everything into sines and cosines again. A lot of times that kind of helps you to see what's going on. So the first thing I would do here, secant. Secant is 1 over the cosine of x minus tangent. tangent is the sine of x over the cosine of x times the sine of x. Now, just to help me, I put a 1 underneath so I make sure that I remember that that sine is on the top. I want to prove that this whole thing is just 1 over the secant of x. Well, looking at this, I'm like, oh, it kind of looks a little bit yuckier now. However, I notice that I'm subtracting fractions. In order to subtract fractions, you have to have a common denominator. Well, order of operations, I'd multiply these first. If I multiply these, I will have that common denominator so I can subtract. I would have 1 over the cosine of x minus top times top. Sine of x times sine of x is sine squared of x over cosine of x times 1 is cosine of x. Now I can subtract these because I do have a common denominator. Cosine of x would carry. On the top, when I'm subtracting, these are not like terms. So I would write both the 1 minus sine squared of x. Now I want to prove that it's 1 over a secant of x. I'm not there yet. Remember, when you see a power of 2, that's going to bring us to one of those Pythagorean identities. There's only one Pythagorean identity that contains a sine squared. It looks like this. Sine squared of x plus cosine squared of x equals 1. I have 1 minus the sine squared of x. So I have this identity, but the sine squared of x was moved to the other side. So what I would have is cosine squared of x equals 1 minus sine squared of x. Now notice that's what I have. That's my numerator. My numerator is 1 minus sine squared of x. This tells me that it would be the same thing as if I wrote it as cosine squared of x because they're equal to one another. So I can change 1 minus sine squared of x into cosine squared of x. Bottom is cosine of x. I have 2 cosines on the top, 1 on the bottom, so I can cross 1 off the bottom, 1 off the top. That leaves me with the cosine of x. I want the secant. Well, 1 over the secant means what is the reciprocal of secant? The cosine is the reciprocal. The cosine is the same thing as 1 over the secant of x because they are reciprocals of one another. That was number 1. Okay, now number 2. Number 2 was my favorite one. If you remembered from Algebra 2, when we did Chapter 6 talking about polynomials and then we looked at rational functions, remember if you have a polynomial over a monomial. And what that means is I have monomials separated by plus and minus signs as a numerator, but the bottom is only one term. You are allowed to separate that into individual fractions. What that looks like, I would take 1 over the sine of x plus sign. Then I could take cosine of x over the sine of x. Now check this out. 1 over the sine of x means what's the reciprocal of the sine of x? Well, that's the cosine of x. Plus cosine of x over the sine, that is the cotangent of x. These two things matched, you completed the proof. Okay, number 3. I hope I'm not going too fast here, but the cool thing is, since you're watching a video, you can totally like pause or whatever you need to do. If you get sick of me and you need to hit pause and go for a walk and take a break, I won't even know it, so it's kind of funny. Okay, let's look at the next one. Now, number 3, to me, is probably the most challenging of all, because look at that thing. I have a fraction, and I'm multiplying on the top of the fraction, and I'm adding on the bottom of the fraction. Lots of crazy stuff's going on. When a problem looks like that, and it might feel a little bit overwhelming, I find it easier to think about it in 2 separate pieces. So step 1, I'm just going to look at the top. The top secant, if I go into sines and cosines, the secant is 1 over the cosine times the sine. Now, since the sine is not a fraction, I have to remember that it's really sine of x over 1. So this is sine of x over the cosine of x. That's the top. I can leave it like that, and that's what I'm going to do at this point. Okay, if I need to later, I know that the sine of x over cosine of x is tangent. I could turn it into the tangent, but at this point, like I said, I feel that it's easier if it's sines and cosines. So there's the top. Now let's battle the bottom. Sounds like a video game. Tangent of theta plus cotangent of theta. Notice what I did here. I'm switching to x's and thetas, and oh my goodness. Okay, tangent of theta plus cotangent of theta. Tangent is sine of theta over cosine. Cotangent is cosine of theta over sine of theta. Now in class today, we had a few people that wanted to cross cancel. Remember, you cannot cross cancel unless you're multiplying. Here they're asking us to add. You cannot add fractions unless you have a common denominator. I need to create a common denominator for these two fractions. Your common denominator would have to contain both a cosine as well as a sine. Now when I look at the first fraction, I have the cosine, it's missing the sine. I need to multiply the first fraction by the sine of theta. And remember, if you multiply on the bottom, you also have to multiply on the top. The bottom, when I multiply, what I did is created that common denominator. On the top, sine of theta times the sine of theta is sine squared of theta. The second fraction has the sine. What it's missing is the cosine. So I would need to multiply top and bottom of the fraction by the cosine of theta. Sine times cosine would get me the common denominator. Cosine times cosine would be cosine squared. When you are adding fractions, your common denominator would stay. So cosine of theta, sine of theta. On the top, when I go to add, these are not like terms, okay? So I have to write them both as the numerator. So sine squared of theta plus cosine squared of theta. This is a Pythagorean identity. The sine squared of theta plus cosine squared of theta is 1. So I really have 1 over cosine of theta, sine of theta. Now I'm not done. What I did is I simplified the top and I simplified the bottom. Now it's time to put them together. The top, I need to make sure I go back to thetas here. Sine of theta over the cosine of theta. On the bottom, 1 over the cosine of theta, sine of theta. I cannot divide fractions, so I keep the top the same. I change divide to multiply, flip the second one upside down, so it's the cosine of theta, sine of theta over 1. I have a cosine on the bottom and a cosine on the top. I cannot cancel anything else. The sine times the sine is the sine squared of theta. That's what we were trying to prove. If I look back, I wanted to prove that all of this, the secant of theta times the sine of theta divided by tangent of theta plus cotangent of theta, all of that actually results in just a sine times a sine. And we did that, okay? Next one, again, I tried to do a couple tricky ones back to back just to kind of show you that you can do this, okay? I promise you can do this. If I look at number 4, yes, it looks a little bit intimidating because I have 2 fractions, I have all these crazy trig functions. Again, just like last time, we looked at the top first and then the bottom. This time, do the same thing, but look at one fraction at a time. So if I'm only focusing on the first fraction, the secant is 1 over the cosine. Divided by, I'm keeping it as a cosine because I'm going with my little rule, change it all to sines and cosines when you can. So I took the first fraction, this is what it would look like. I can't divide fractions, so I keep the top the same, change divide to multiply. When I do the reciprocal, I have 1 over the cosine of theta. When you multiply fractions, top times top, 1 times 1 is 1, bottom times bottom, cosine times cosine is cosine squared of theta. So there's the first one. Minus, because notice we're subtracting fractions. The second one, I'm going to do the same exact thing, okay? What I want to do is change it all to sines and cosines. So tangent is sine over cosine, so sine of theta over cosine of theta, over the cotangent, that's the reciprocal, so the cosine of theta goes over the sine of theta. Again, I can't divide fractions. That doesn't work. So what I need to do is keep the first fraction, so my numerator stays the same. Change divide to multiply, flip the second one upside down. That becomes sine of theta over cosine of theta. Now when I'm multiplying the fractions, top times top, bottom times bottom, sine times sine is sine squared of theta. Bottom, cosine times cosine would be cosine squared of theta. Here is the cool thing. When you look, I am subtracting fractions. In order to subtract fractions, you need a common denominator. We have that. Your common denominator carries on over into the solution. What I'm subtracting are the numerators. These are not like terms. So I would take 1 minus sine squared of theta. Well, we're trying to prove that this is a 1. Okay, so if I look at that top, I need to figure out, well, 1 minus sine squared of theta, what is that? I see a power of 2. So that brings me to my Pythagorean identities. Remember, we have one that has a sine squared. There's only one. It says sine squared of theta plus cosine squared of theta equals 1. If I rearrange this, I can get it to match 1 minus sine squared of theta. I just have to take the sine squared and minus it to the other side. So what this shows me is the cosine squared of theta has a value of 1 minus sine squared of theta. So by rearranging this, it tells me that if I have 1 minus sine squared of theta like we do, I can replace it with cosine squared of theta. So the numerator is really cosine squared of theta. The bottom is cosine squared of theta. Cosine squared of theta divided by cosine squared of theta is a 1. That's what you wanted to prove. Okay, let's look at number 5. Now number 5, this was one where I even first looked at it, I'm like, oh boy, where do I start? Okay, if that happens to you, totally fine. I do want to go ahead and show you. Remember, I always practice all the assignments. Okay, so here were my notes when I was practicing. I want you to notice here I tried something. It didn't work, so I crossed it off and had to try something else. Here, I tried something. It got me nowhere, so I wrote nope, put a little sad face, tried something else, crossed it off. One thing that is really, really hard with this type of problem is there is no right or wrong way to start this problem. You just need to dive in and realize sometimes you might get so far and then realize, okay, I'm not getting anywhere, and be okay to say, all right, that didn't work, and start over and try something else. And I know when I was in school, that was so difficult for me because I wanted to know the right way to do it, okay? There is not a step-by-step right way. There's lots and lots of different ways that you can do this. You just work with one side until you get it to match the other. Even after teaching this for years, I get stuck and have to start again. So if that happens, please do not beat yourself up. Do try your best. I would say don't get frustrated, but I know the feeling, okay? So try to not get frustrated. Know that you're just learning this. And when you do get stuck and then when you figure it out, you actually probably did a better job of learning something new. A lot of times when you are learning, the best way to learn is to make those mistakes and learn from those, okay? So let's just keep on going, but there was like a little mental break for you. Okay, now like I said, number 5, when I was practicing this, I was like, oh boy, because they're already sines and cosines. So when that happens, what I tend to do is say, all right, I'm looking at this side. I want it to match this side. Well, this side has a cosine, but I want my final answer to only have sines. This is a cosine squared. So again, remember, sine squared of theta plus cosine squared of theta equals 1. That's a Pythagorean identity. If I want to get cosine squared of theta by itself, I would just have to minus the sine over. So I can take any cosine squared of whether it's theta, x, or y, and I can replace it with 1 minus sine squared of theta because these two things have the same value. So that's what I did here. I took cosine squared of y and said, all right, instead I'm going to say 1 minus sine squared of y. That's just this part. Then I still have minus sine squared of y. I can combine like terms. Negative sine squared of y minus sine squared of y is negative 2 sine squared of y. That's what I wanted. Okay, number 6. Number 6. Again, here my initial gut feeling is get everything into sines and cosines. Sometimes it works, sometimes it doesn't. This time I believe it did. If I have cosecant squared of theta, cosecant is the reciprocal of a sine. Because this is cosecant squared of theta, when you do the reciprocal, it's 1 over the sine squared of theta. Times tangent is sine over cosine. Because it's tangent squared, it's sine squared over cosine squared minus 1. Sine squared on bottom, sine squared on top. So I have 1 over, what am I doing here? Oh, there we go. 1 over cosine squared of theta minus 1. So see, even now I'm like, oh, what's going on? Well, 1 over a cosine means this is really the reciprocal of the cosine function. The reciprocal of the cosine function is the secant function. Because this is cosine squared, this would be secant squared. Well, I want to prove that this is a tangent. So I need to go ahead and look at one of these Pythagorean identities. And again, these are on the notes that we looked at yesterday. I need to find a Pythagorean identity that has secant squared and see what's up. There's only 3. Only one of them will have secant squared. So here's what that identity shows. 1 plus the tangent squared of theta equals the secant squared of theta. I have secant squared of theta minus 1. What happened is this 1 got subtracted over here. When the 1 got transferred over, what I had left was tangent squared of theta. That's what we want to prove. So secant squared of theta minus 1 is tangent squared of theta by that Pythagorean identity. We just had to rearrange it. Okay, 2 more. I know this video is getting a little bit long. However, I do feel it's important to go ahead and go through all of these examples. What I did for grading, because I did every example with the class, is I am giving you participation points. You just need to show me that you did try and complete all these questions and you get a 10 out of 10. Then your assignment for today is to try 8 new questions on your own. The difficulty is in between what we looked at on the front side and the back side, okay? So please make sure that you do complete this worksheet, both front and back. Turn it in. I'm giving you completion points, and then I will give it back to you so you can keep it as a reference, okay? Let's go ahead and look here. Number 7, I have secant squared of theta minus 1. Now, I get excited because I'm like, hey, on the last example, we just learned that secant squared of theta minus 1 is the tangent squared of theta. So immediately I got really excited and I said, I know that the bottom is really a tangent squared of theta, because that's what we did in the previous problem, is we used that Pythagorean identity to prove that. Now, secant squared, secant is the reciprocal of the cosine, so it's 1 over cosine squared of theta. Tangent is the sine over the cosine. Again, make sure that you have sine squared of theta over cosine squared of theta, because the tangent was squared. Keep the top the same, 1 over cosine squared. Change divide to multiply. Flip the second one upside down so it becomes cosine squared of theta over sine squared of theta. Cosine cross cancels cosine. 1 over sine squared of theta. 1 over means the reciprocal of sine. Well, the reciprocal of sine is the cosecant squared of theta. That's what you tried to prove, so we're done. Last question, and you made it. Here was one that I thought was like, okay, I'm going to do this. Okay, I'm going to be honest. This was one where I wrote, nope, I think I tried 3 different things before I figured this out. My initial gut feeling is I said, let's go sine squared of x over cosine squared of x and multiply it by sine squared of x. Well, that didn't work because then I'd have 4 sines. I'd have sine to the power of 4x. So I did a big nope and a little sad face, okay? So if you did that, that's okay. I've been teaching this forever, and that's what I did first. I noticed that I want a minus sign. So at this point, I went back to that whole thing where I know that the tangent squared of x would be secant squared of theta minus 1, because I worked with that in the last 2 problems. So I was like, well, let's go ahead and use that and see if that works. The reason why I did that is because it would be putting a minus in the problem, and I want a minus in my final solution. So I changed the tangent into the secant squared of x minus 1, because this is equivalent to this based off of the Pythagorean identity. Then we're multiplying it by the sine squared of x. You can multiply trig functions. This is 2 terms being multiplied by 1 term, so I need to go ahead and distribute. So the secant squared of x times the sine squared of x minus sine squared of x. Well, secant is 1 over the cosine. If I multiply it by the sine squared of x over 1, I'm going to leave this as the sine squared of x, because if I look, it's actually the second part of what I'm trying to prove. Top times top, bottom times bottom. Sine squared of x over cosine squared of x. Sine over cosine is the tangent, because these are both squared, so it's tangent squared of x minus the other side was sine squared of x. You just proved it. And that's exactly what we did in the classroom today. We just went through the entire worksheet, both sides, step by step, and then the assignment is a new worksheet. It is just a front side where you are trying 8 new questions. I hope this helped you to feel a little bit more confident in proving trig identities, and I hope to see you soon. Bye.